which meets the axioms, and also allows me to define an important property, an important probability, the probability of not exceedance. Okay, then let me say, and then we are getting out of this difficult step, that this is the cumulative probability. It's called cumulative probability. And again, unfortunately, I'm using the same symbol, but I didn't want to change it for the cumulative probability and the probability of getting a value, a fixed value of a discrete variable. They are different things. So keep in mind, one thing is a discrete variable, where you can get the probability of each outcome. One other thing is a real variable, where you need to define the probability density to obtain the cumulative probability, which is what you are interested in. Keep in mind that the cumulative probability and the probability density, they convey the same information. Same. There is no difference. And one is the derivative of the other, or the integral, you see here. So basically, let me say that you may write that P of Qi is equal to the derivative of let me say, first of all, that the probability density of Q is the derivative of the cumulative density of Q in the Q. Sorry. And yes, if you compute it in Qi, you get the probability density of Qi. Yeah. Can you see behind the screen? Let me see it first. Look, this treatment, and now we are ready to stop again, allows you, given a series of river flow observations, allows you to compute the probability density. It's very easy, because if you have a series of observations, it's very easy to compute the probability of not exceedance. Let's suppose that you have a series of 1,000 values of river flow, and you see that the river flow of 100 is not exceeded for 900 times. Then the probability of not exceedance is simply 0.9. And you can do this computation for any river flow value within the range of the observations. So the probability of not exceedance can be computed empirically in a very simple way. So you can very simply draw an histogram of the probability of not exceedance. Let me delete this and draw this histogram. So let's suppose that n is, as I said, is equal to 1,000. And then let's suppose that here you have the range of river flows, and let's suppose that it's varying between 0 and 132, which is the maximum observed. And then you can write here the probability of not exceedance. And of course, for any value that is included here, whatever, let me start from 1. You can start from 0. How many zeros do you have? Do you have 10 zeros? Okay, then the probability of not exceedance is here. And then you go to 1, and you get another value here, and another one here. And typically you get a step function you get a step function, but keep in mind that you can decrease the delta Q, as you want. So it's a step function, but thanks to the computer, you can reduce the width of the steps as you want. And therefore, once that you have an estimate, an empirical estimate of the capital P, cumulative probability, no, sorry, this is wrong, because the cumulative probability is always increasing until 1, sorry. Of course, it's always increasing. Okay. What I depicted before was the density. This is the cumulative probability is always increasing, and typically it takes different shapes, but once that you have defined this function empirically, then you can compute the derivative. And the derivative typically looks like this. Let me depict once again here PQ, capital P, cumulative probability. This varies between 0 and 1, and this is Q, and this is Q max. So basically you have to get to 1 here. And the typical shape that you may have is something like this. Usually you increase very smoothly, not much at the beginning, and then you have a central part where you have many observations, and therefore if you have many observations you have a rapid increase of the cumulative probability, and then you get a picture like this. And let's suppose now that you want to depict here the lowercase bq, and the derivative of this function is functions like this. It's the slope, you know, this is, the derivative is the slope of this integral function. And of course you have the highest density in the middle of the range, typically, around the mean value. Probably should have been shifted a bit on the right, this one, because the highest density is in correspondence of the highest slope. It should be here, okay? So basically, through the definition of cumulative probability, you can easily define, you can easily estimate the probability density by taking the derivative. This is done empirically. You can do it empirically. And tomorrow with the R, I'm not sure we will have time because I also want to apply IMOD, but it's very easy with R. I want to make such an experiment because it's really very easy to build these histograms. Okay, this is, I would say, one of the most difficult steps in understanding statistical models. So once that you got this definition of probability, cumulative probability and probability density, you are at a good stage. Now there is another thing, which is, it would be useful to have an analytical relationship to describe these curves, because I estimated them empirically. And you know, an empirical estimation is fine, but there is a problem with the empirical estimation that, of course, you can't estimate the probability for whatever value of the river flow, because otherwise you have infinite values. So it takes too long. You have to stick on fixed values. And how to interpolate between the values where you estimate the probability, you need an analytical relationship for those curves. So even if you speak of the cumulative probability or the probability density, it would be very useful to have an analytical relationship describing these curves. And once that you have an analytical relationship for one of them, you get also the analytical relationship for the other one, because it's just a matter of taking an integral or a derivative. So it would be very useful to get an analytical relationship, and then statistician, what did they propose? They proposed the probability functions, which allows you, it's a mean to allow you to skip this empirical estimation. You use an analytical relationship to express the probability. Of course, it must be appropriate. The analytical relationship should provide a good interpretation of what you find empirical. And now next hour we will see this. I will stop again because it's too noisy.